Hi everyone. Today we are going to be introducing a vital concept of applied calculus, optimization. The idea of optimization is finding specific values where another specific quantity is maximized or minimized, depending on what the scenario is. So, here's the question. A homeowner buys 750 feet of fencing to build a rectangular backyard. So this is his backyard right here. What is the maximum possible area of the backyard? So the thing we're trying to maximize here is the area, this whole region right here. How many square feet is the maximum possible area? That's what we're looking for. But here's a constraint we have. The amount of fencing he has is 750 feet. So let's go ahead and label some quantities here so we know what this is really trying to say. So this is a wall, meaning that this does not take up any fencing. This is first part of fencing. This is the first part of the fencing, which we'll call X. And since this backyard is rectangular, if this side is X, then this side is also X. And this side right here is not necessarily X because we don't know that this is a square. So we're going to call this side Y. So here's the constraint we have. The total amount of fencing here should add up to 750. So the constraint function, we will say, is that x plus y, or 2x plus y, is equal to 750. All right? So here's the equation we need to optimize. The area of this, which we can calculate as length times width, which is x times y. So the area is equal to xy, which is equal to, we don't know what it's equal to. We're trying to figure out the maximum possible quantity. So how can we go about doing this? We need to find some way to maximize this equation. Well, let's take a look at it from a graphical standpoint. So let's say we have some arbitrary graph f of x that looks something like this. So this is our f of x. This area right here looks to be a certain maximum. It looks to be a maximum value over a closed region. Let's say we pinpointed our focus to this area right here, which is, let's say, like from A to B, right? This point right here indicates a local maximum over this interval. So here's a special characteristic about these points. This goes for local maximum, local minimum, and a special type of point, which is a stationary inflection, which we'll get to later. This right here has a tangent line. This right here has a tangent line with a slope of 0, a horizontal tangent. That is the fundamental characteristic of a maximum or a minimum, or again, a special miscellaneous point, which doesn't really matter for this. So we need to find some way to treat this as a function, a equals xy, and then find the point where the derivative of this function is equal to 0. Because again, the derivative represents the slope of the tangent line. So to get a horizontal tangent line, the slope of that must be 0, hence the derivative must be 0. So here's what we're going to do. We're going to treat this like a system of equations, where we have this unknown quantity a, which is what we're solving for. So let's find a way to just isolate either x or y. Y doesn't have a coefficient, so we're just going to do that. So let's take this math over here. So we get y is equal to, if we move 2x to the other side, we get 750 minus 2x. And now what we're going to do is we're going to take this expression for y and plug it into this area expression right here. So the area is going to be equal to x times 750 minus 2x. This is our new area function, and we can see we have it in terms of one variable. So in other words, we can treat this as a single variable function, such as this f of x right here. So first things first, we're going to go ahead and just distribute this x in. So that gives us 750x minus 2x squared. And now we're going to go ahead and take the derivative of this function and set it equal to 0. That way, we will get a certain x point that gives us a horizontal tangent, which is what we need to find a maximum or minimum. Well, in this case, we know it's going to be a maximum, right? Because, here, I'll go ahead and show you first of all why it's a maximum. So this function, 750x minus 2x squared, is actually a downward facing parabola. You can tell because this has a negative coefficient multiplied to x squared. So the graph of this function is going to look something like this. Obviously this is probably completely wrong, but that doesn't matter. And this point right here, which we recognize from algebra 1 as the vertex, this is a maximum point for this parabola. And again, the defining characteristic of the maximum in calculus terms is that the derivative or the horizontal or the slope of the tangent line is 0, giving us the horizontal tangent that we need. So let's go ahead and differentiate this function with respect to x. Take the derivative. So this is going to give us dA over dx, or you can notate it as a prime, it doesn't matter, is equal to 750 minus 4x, which equals 0. So now all we have to do here is just solve for x. So x is going to be equal to, if we go ahead and move this 4x to the other side and divide both sides by 4, we get that x is equal to 750 divided by, 750 divided by 4, and let me try and mental math this real fast. This should equal 187.5 feet. And then what should y equal? Y is going to be equal to 750 minus 2 times 187.5. Wait, let me actually make sure that this is 187.5. Yeah, okay, it's 187.5. Cool. This is going to be 750 minus 2 times 187.5. This should be equal to 750 minus 375. And then y works out to be 375 feet. Now, if the question had just asked for the dimensions that would maximize the area, if that was the question stem, we would have our answer here. This would be a 187.5 feet by 375 feet a backyard. That's the word I was thinking. Sorry. But what we need to do now is multiply these two quantities together to get the maximum area. Now, I don't have a calculator on me. Feel free to figure out what the answer is on your own. I'm just going to leave it as like the simplified version. So the answer you should get is 187.5 times 375. And this works out to be 375 squared over 2. Whatever this quantity equals. I don't have the calculator on me. I don't know off the top of my head what 375 squared is. So 375 squared over 2 feet squared. And this right here is your maximum area. Now feel free, typically if you don't have a calculator for these problems, you're probably going to be asked a question with easier numbers to work with. You'll probably see something like 60 feet instead of 750 feet. But if you had a calculator, you would probably see this number come up, or even unfriendly numbers like 1,872. That might be a number you might see. So if you have a calculator, feel free to figure out what this quantity is, and that will be your answer. Typically in calculus, you want to round to like 3 decimal places, and you can just go ahead and put that down for your answer. Problem solved. And so that's basically the most introductory problem to optimization. In further optimization problems, you'll see much harder, more abstract concepts. There's going to be stuff about particle motion, which we'll get to in future videos, and even curved distances from curves. We'll see that. But yeah, this problem right here is the most fundamental introduction to optimization. And that concludes this part of the optimization series. I forgot to mention, this is going to be a part 1, and we'll be doing harder problems in future videos. So I hope to see you then.